Today I'm going to show you the next iteration of my robot arm, the Mark III. Still based on a linear actuator design, but this time there's only a single actuator, but it's connected to this parallel structure which allows all the other axes to act in the horizontal plane using a Scarra style arrangement so that they don't have to work against gravity. Designed mainly for a domestic situation rather than a precision pick and place situation, I've chosen to use Dynamixels rather than stepper motors because there are several advantages, mainly to do with the simplicity and size. I don't need to add additional drivers or communication channels other than the serial link. There are other advantages such as torque feedback, so the gripper here can choose to apply different torques based on the size or the weight of the object that it's trying to pick up. There is a little bit of slop in the system. Compared to a stepper motor, there's a few degrees of movement here. This can be controlled by the Dynamixel compliance curves, but I'm using the default values here, but I expect some tuning could be done. I think the advantages of the stepper motors are much less in an unstructured environment where it's possible that the objects could be placed anywhere, so the open loop feedback without feedback is not as useful. I'll give you a quick demonstration of it here, picking up two different styles of objects. First it tries to pick up this full bottle of water over a kilogram in weight. Has no trouble at all picking it up, lifting it, dropping it or gripping it. And next it'll pick the banana up. Here it uses a very small amount of torque, and the system senses when the gripper is finished moving so it can move to the next phase of operations. So I think that's a pretty successful demonstration. The linear actuator here is connected in series with a spring to provide some compliance. The spring, similar to this mechanism here, where it pulls against on a moving rail. This has a couple of advantages, both in safety, stopping the linear actuator from driving too hard, too fast into something, and also allows me to use a linear pot here to measure the displacement and therefore the force. This allows me to use the actuator for training in position, so I could move it by hand. Dynamixels are easy to train. If I put the put training mode on here, it just disables the torque. I can just move the arm by hand. But if I apply some upwards force, the potentiometer detects the displacement and drives the actuator in the direction of the force, which means that I can position the arm pretty much however I want using simple movements. It also allows for some interesting possibilities in power assist. If I connect a heavier load to the system here, not on the arm itself but just above it, there we go. So that's a 2 kilo weight there. If I put it into train mode and just move it slightly, the system can detect the change and move the weight up using a minimal amount of force. There's also an estimate for the weight here. You can see 2 kilos, something like that. This is just a rough estimate. Interestingly though, the weight depends only on the angle of the parallel mechanism and not the actual radius of the scarra part of the arm, because the additional weight is borne by the mechanical components of the system. The joints themselves are 3D printed using something like this, which contains two ball bearings which have a 12mm hole in the middle, and then I just connect normal 12mm bolts through the middle to act as an axis, and coupled to the Dynamixel using a simple 3D printed sleeve. The arm itself is screwed onto the wall. I actually quite like this because it clears up the desk space below. I could use a rotation mechanism there, which would actually probably double the range of the arm. It would also keep the mechanism all horizontal, but I don't think I need the extra range at the moment, so quite happy with this arrangement. The driver is driven by just a 12-volt power supply straight into the Dynamixel bus, and a PC connection to an OpenCM 904 chip. I like this board because it has 4 serial ports. Its serial ports, I use one to talk to the PC, one to talk to the linear actuator motor driver over a serial system, one to talk to the Dynamixels, and the last one is connected to the Zigbee, which allows the remote control to move the arm in the various directions based on the button inputs. I intend to replace that with a Bluetooth system talking to a vision system in the future, and I think that'll be quite a nice way of going. The Dynamixels themselves are also connected at the lowest power end of their capabilities, using 64 out of a possible 1000 speed settings. If I just crank that up, you can see the arm can move much faster than I was moving it earlier, but I think probably dangerously fast, and especially with a large inertial load. I don't think there's much point in using the high speed movement. So I'm pretty happy with this design. I think some room for improvements. The gripper itself is just made with some elastic band glued onto some 3D printed parts, and in fact I need to set the Dynamixel power above 20% in order to get it to move the gears against the static load. So I think some more work could be done there, perhaps some better bearings, but just using nails at the moment. Also, I think a couple of extra degrees of freedom would be useful. But generally, this design is meeting my goals of sort of reach and load that I was trying to achieve, and I'm pretty happy with the way things turned out. If there's any comments or questions, you can leave them in the comments of this video, and I'll try to get back to you. I hope you've enjoyed this design.